Okay, so in today's session, we are going to discuss the images or ray diagrams formed when the object is kept in front of the concave lenses. We already have seen how images, that is ray diagrams, are formed when the object is kept in front of the convex lens. Now we are going to learn the same thing, that is ray diagrams in front of or due to the concave lens. A concave lens is a type of lens in which the middle portion of the concave lens is, I can say, or we can say thin, and at the periphery it will be expanded. Okay, so this type of lens we call it as a concave lens. For drawing the ray diagrams, few rules has to be obeyed, like one line will be passing through the center of the concave lens and it is called as the principal axis. So I mentioned here that principal axis. Then after that, this point is denoted as a O. Just make a dotted line here. So we can say this is the plane from which the refraction occurs. Take a certain distance, make a point F, similarly let's say F1, and from the same distance OF1 to F1 F2, that is twice of F1, and in the right hand side it will be F2, same distance, as if that means F1 and F2 are equidistant from point O, and from F1 to F2 same distance. Now there are three diagrams that we have to learn. That is, first is object at infinity. We saw that when the object is at infinity and kept in front of the convex lens, the image is obtained at focus, and that image nature was real and inverted. Suppose if we keep an object, so when the rays of light that is coming from the infinity, that will be parallel to the concave lenses like this. This is the first extreme ray, or this is the another ray, extreme ray in the lower section, and all the other rays will be parallel in this way. Since the object is at infinity, rays are traveling parallel to each other almost, and it will strike to this dotted line, we can say, that is the plane of the concave lens, and they will be directed away from the path from each other. And if we see them, we observe that they are actually moving away from each other, but if we extend them, we feel that all the rays are actually emerging from the same point. This point we call it as the focus. That means when the object is kept at infinity, its image will be obtained at focus, that is left hand side of the concave lens. But this image is not actually formed by the actual refraction, rather we are extending the refracted ray backward direction, and we are forcing these rays to meet at a particular point. That's why this kind of the image we call it as a virtual, and also it is erect. Okay, since virtual image cannot be shown on the proper screen, and the image that we will be getting will be virtual. So image virtual and erect. If you ask what is position, position will be at focus, you can say F1, and size, again it will be point size, or we can say almost tiny. Okay, suppose if we take another image, this is a concave lens, and now we are considering the image which is beyond 2f1. That is, we are just bringing that image towards the lens. We are keeping an object somewhere here. Let's say this is an object. Name that object is AB. Obviously, the first rule, if we allow it refracted ray to move parallel, we observe that there is a refracted ray, and if we allow that light to pass through the optical center, it will be undeviated or undisplaced. It will move as it is. Okay. So here also we are observing two rays are moving away from each other. If we force them, as we know that this ray will be appears to be emerging from the focus. This will be your A dash and B dash. So this is another image formed in front of the concave lens. If we keep an object in front of the concave lens at a distance beyond 2f1, so in this category, if I say image, that will be the virtual and erect again. Position will be altered, that is between O and f1. That means left hand side of the lens between O and f1, and the size will be smaller than object, or we can say diminished. Okay, so this is another category of the type of the image. After that we have one more image, that is when the object is kept at focus. If the object is kept at a focus, or some other images, for example, so by observing these two ray diagrams of concave lens, we can say that whenever the object is kept in front of the concave lens, the images that we are getting are said to be virtual and erect. Okay, that means the object's image we will be getting in the left hand side of the lens only. The first object, when it is kept at infinity, the image is formed at focus, and the object is kept between optical center and the that means we can say to the far point, or beyond 2f1, the image that we are getting between optical center and focus. So table is given on page number 117, that is the relative position of the object and image in a concave lens. Now we discuss one small point that is given in your textbook. What do you mean by, or what is the difference between the real image and the virtual images? All real images, we can say, they can be put or they can be shown on the actual screen, and such type of images are real, or we say erect. Okay, and the images which are not able to put up in front on the screen, so we say that it's virtual. That means real images are formed by the actual or real refraction of the incident rays. They actually meet after the refraction to the particular point, as we saw in case of convex lens, except one image when the object was kept between optical center and focus. Otherwise all the images were real and inverted, because these images were formed when there was an actual refraction of the incident rays and they are meeting at a particular point, and that's why we are getting the images. But in case of virtual image, the incident ray after refraction actually diverge. That means in case of concave lens. But if we allow these rays to move in the backward direction, we can show that, or we can see that there is a point from which these refracted rays are emerging, and or we can say from which it is diverged. So such kind of images we call it as a virtual. As I told you, real images can be seen on the screen, virtual images cannot be seen on the screen. The images formed by the convex lens, mostly they are real and inverted except one case. Otherwise the images formed by concave lens will be virtual and erect. So you have differences on the page number 112. So here I can say that now we finished our 5.2, or we can say 5b part, and now we can move to the 5c. That's it. Okay, in the 5c part, the first part is given as a sign convections. Now take any one lens, that is convex lens or whether it is concave lens. In both the types of lenses we have an optical center, and it is denoted as a capital O. But if we consider that optical center as a origin of the geometrical axis, okay, this is the geometrical center, or we can say optical center in case of convex, and in concave we have optical center here, as there is an imaginary ray passing through the optical center, and we call it as a principal axis. So if we choose this optical center as a geometrical center of a geometrical axis, the images, they are actually, or we can say the object is placed in the left part of the optical center. Object will be kept in the left hand side of the lenses, and the distances in the left hand side will be taken as negative always. As we know that in the coordinate geometry, the distances in the left side is taken as negative, distances in the right side it is taken as positive. Similarly, the distances measured above the principal axis or length above the principal axis is termed as a positive, while the lengths below the principal axis termed as negative. So there are some sign conventions given for each of the lenses. Both lens, there will be a same sign conventions, that optical center will be considered as a geometrical center, and all the distances such as the distance of an image from or the distance of an object, all the distances are measured from the optical center. The distances in the left hand side of the optical center, or we can say of the lens, is considered as a negative, while the distances in the right hand side of the lenses are taken as a positive. Similarly, there is an imaginary axis, we call it as a principal axis, passing through the optical center. It is already normal to the position of the lens, and the distances above the principal axis will be taken as a positive, while the distances below the principal axis will be taken as negative. Apart from that, we have two more sign conventions, may not be included in this part, that the focal length of the convex lens is considered as a positive, while the focal length of the concave lens will be considered as a negative, because the focus where the incident ray after refraction meet, in case of convex lens it is in the right hand side, while in case of concave lens it is in the left hand side, so they will be taken as a negative, and for convex lens it is positive. Okay, and apart from that, we have two more points that is to be that need to be included, that is the lens formula and linear magnification. So lens formula will be given as 1 upon v minus 1 upon u is equal to 1 upon f, where this v stands for distance of an image from the optical center. It will be positive if the distance, if the image is in the right hand side, that means real image. Okay, and in case of the concave lens where image is getting in the left hand side, this v also will be negative. U is always negative because object is always in the left hand side of the lens. U is called as the distance of the object from the optical center, and this f we call it as a focal length, that means distance of the focus from the optical center. Okay, and after that we have one formula, that is linear magnification. This is actually a mirror formula, mirror, oh sorry, a lens formula. And we also have linear magnification, that is the word magnification, you know how much magnify image with respect to object, that means the ratio of size of an image to the size of an object. Okay, that is h2 upon h1. Okay, that is called as magnification, denoted as m. And this h2 upon h1, surprisingly we will observe that it is equal to v upon u, where v is the distance of an image from the optical center, where u is called as distance of an object from the optical center. So this ratio will always be equal whether it is convex lens or concave lens. So this is called as linear magnification, ratio of size of an object to the size of a ratio of size of an image to the size of an object. That's it. Come to the last part, that is power of the lens. As the word power means, there are two types of lens we know, convex and concave. Convex lens, we see converging of the incident ray at a particular point, and in case of concave we observe it, there is a divergence or diverging lens we also called as. So the ability of a lens to converge or divert, that we call it as a power. So the formula for power, it is given as 1 upon f, that is inverse of its focal length, but focal length should be included in meter, and its unit is given as diopter, denoted as a D. Obviously P will be plus positive in case of convex lens, because at ultimately focus is positive, and in case of concave lens it is negative because its focal length is negative. Okay, suppose I give an example. Focal length of the convex lens is plus 20 centimeter. This plus indicates that it is a convex lens. We need to convert it into meter. You need to convert it into meter like 0.2 meter, and take the power. Power is 1 upon 0.2, and answer should be plus 5, as the value is positive, plus 5 D. If it is concave lens, the power will become negative. So the power of the lens is the ability of a lens to converge or diverge the incident rays whenever these rays will be falling on the particular lens. This part's numerical is excluded from the syllabus. So only the formula and the definition you should remember. Even other derivations are also excluded. Whether derivation for lens formula is also excluded. So we are only having the definition and formula, and in case of power of lens, numerical will also be not there. But in case of mirror formula, lens formula, sorry, you will have some numericals. Okay, that's it.